Hi, welcome to video 9.6b. These are mixed tests, and we are now finished with all of the convergence and divergence tests for infinite series of constant terms, numbers only. And now's where we're going to really look at which one we use when. Okay, so on page 648, numbers 51 to 68, it says determine the convergence or divergence of the series using any appropriate test from this chapter and identify the test used. So this is like number 52. So 5 over n, very easy. Pull out the 5. It's 5 times the harmonic, which is 5 times divergent, which is divergent. This is like number 54. If you write it out, you'll notice it's a geometric series. The common ratio is pi over 4. Keep in mind that's 3.14 over 4. Since the absolute value of r is less than 1, the series converges. They don't ask you what it converges to. They just want to know if it converges or diverges. Limit comparison test, just a quick review. Okay, limit comparison test, you're going to compare it to a series Vn. If the limit as n goes to infinity of un over Vn is a positive constant, then both series converge or diverge. If it's equal, the book will say this. The book doesn't tell you this part here. If it's equal to 0, and if the series you're comparing it to is convergent, then your series will be convergent. If it's equal to infinity and the series you're comparing it to is divergent, then your series will also be divergent. Okay, so right now you'll notice this is no special kind of series, not geometric. It's not a p-series. It's not an alternating series, so we're going to use the limit comparison test. We're going to get rid of the plus 1. We're going to get rid of the 2. We have n over n squared, so we're going to compare it to 1 over n, which is harmonic and therefore divergent. We're going to use the limit comparison test. Our un, n over 2n squared plus 1, divided by our vn. If you divide by 1 over n, you'll multiply by n over 1. And that gives you n squared over 2n squared plus 1. The limit as n goes to infinity of that expression, of course, is 1/2 because these are both polynomials and the degrees are equal, so it's leading coefficient. Since that limit is positive and since the series you were comparing it to was divergent, then your series un is also divergent. Number 58, pull out the 10/3. Rewrite this as n to the 3/2. It's a p-series. The p is 3/2. Since p is bigger than 1, the series converges. So it's 10/3 times a convergent series, which is a convergent. Again, over here, this is no recognizable. It's not geometric. It's not an alternating series. It's not a p-series. So we'll get rid of the plus 1. Get rid of the... Oh, actually, I take it all back. We forgot to think of the nth term test. So if we do the nth term test, we do the nth term test of 2 to the n over 4n squared minus 1. 2 to the infinity is infinity. Infinity squared times 4 minus 1 is infinity. We get to use L'Hopital's. Derivative is 2 to the n ln2 over 8n. I can pull out the ln2 over 8. I'm left with the limit as n goes to infinity of 2 to the n over n. Once again, that'll be infinity over infinity. And then I'll do L'Hopital's again. I'm leaving that ln2 over 8 on the outside. So the derivative of 2 to the n is 2 to the n ln2, and the derivative of n is 1. So now I have ln2 times ln2 is ln2 squared over 8. And of course, I'm left with the limit as n goes to infinity of 2 to the n. Well, 2 to the infinity is infinity. Infinity times a positive constant is infinity. Since that limit does not equal 0, by the nth term test, the series diverges. Number 62, obviously an alternating series. The an, which is 1 over n ln n, are they all positive? Yes, for n greater than or equal to 2. They had to make it bigger than or equal to 2 here because the ln of 1 would be 0 and you'd have a denominator of 0. Are they decreasing? Yes, you could do a derivative and show that the derivative is always negative, or you could prove it. So we're going to try the alternating series test. Find the limit as n goes to infinity of our an, and sure enough, we get in 1 over infinity, which is 0, and therefore, by the alternating series test, the series converges. 69 to 72, I do want you to see that right here, okay? Identify the 2 series that are the same. So they're going to give you 3 series, and they want you to identify which are the same. Now you'll notice they all have an n, either an n factorial or an n plus 1 factorial in the denominator. They all have an n or an n plus 1 times a 5 to the n or 5 to the n plus 1. But you'll notice the limits of summation are different. This one's n goes from 1 to infinity, the other two are 0. So this all comes back. If I take the first one, and I look at what I would do to get from this lower limit of summation to this lower limit of summation, I would have to subtract 4. Well, if I subtract 4 from the limit of summation, then I'm going to have to add 4 to everything else. They did not add 4 here to n. They added 1, and they did not add 4 here. Okay? So these two are not equal. If I compare the second one and the third one, I mean, it's kind of a crapshoot here. I decided with the first and second, and then the second and third. You might decide to go with the first and third. Let's see what happens. As far as the second and third, you'll notice here they've added 1 to the lower limit of summation, which would make them subtract 1 from here, which they did, and subtract 1 from here, which they did. So the two that are the same are B and C. Now, you could write these series out. That would be a very long and tedious way to do it. But if you actually did write these series out, paying attention to the lower limits of integration. Oh, this is number 70, not number 71. So we're doing this one here, number 70. Okay. You could write out the terms of each one and then convince yourself, oh, look, these two series have the same terms. This one does not, but that would be a very tedious way to go. Here's number 72. So again, only two of them are the same. Notice to get from here to here, they subtracted 1 from the lower limit of summation. Therefore, they should have added 1 to everything else. N minus 1 plus 1 is n. N minus 1 plus 1 is n, and these two are indeed the same. You can check the third ones. If you compare the first one to the third one, obviously to get from here to here, they subtracted 2, which would make them have to add 2, but they didn't. So the first and third ones are not the same. You could also check and see if the second and third ones are the same. Here, to get from here to here, they're subtracting 1, which would mean they'd have to add 1, and they didn't. Okay, so just a quick review of the ratio and root tests. It does have to be a series of non-zero terms. They don't have to be positive terms, but they do have to be non-zero. And if the limit as n goes to infinity of an plus 1 over an is less than 1, then the series is absolutely and therefore convergent. If it's greater than 1, and infinity obviously is greater than 1, it's divergent. The problem is if it's equal to 1, there is no conclusion. That doesn't mean you stop and say there's no conclusion. It means you can't use the ratio test. You'd have to go back and use one of the other tests. For the root tests, what you're going to look for is the limit as n goes to infinity of the nth root of the absolute value of n. And again, you'll notice the same conclusions for the root test as there is for the ratio test. It's just a different expression you're evaluating the limit of. But again, if that limit is less than 1, then the series is absolutely convergent. If it's bigger than 1, it's divergent. And if it's equal to 1, unfortunately, there's no conclusion.